Hello, everybody. Yeah, my name's John Morehouse. I'm an architect, and I've been working in sustainability really all of my working life. And a lot of what we do as architects is what's now termed retrofit. If we're working on existing buildings, it's always retrofit. But retrofit has become the watchword for energy and carbon reduction in buildings. Today, I'm going to talk about a particular series of projects that are built on each other, leading to a very successful, well, I think successful, it's complete and it's worked and it was pretty much on budget, a successful SHDF demonstrator project. And I'll talk about the next steps from that and what we're doing on wave 1 and wave 2. So just for the agenda today, we'll talk about a particular case study, which is a Northwest development, and I'll walk you through the visuals and the architectural side of this. I will talk about the targets that we aimed for and hit and how the project came about, the ventilation strategy, the implementation of heat pumps and the challenges therein, how we developed our modelling strategy for this work and how we're now deploying that on all of our projects with a view to working at scale. Talk about the drawing pack and the information we produced and how we're now tailoring that to contractor needs. And then we'll just sum up with the finished product. And I think talk about next steps because we're still dealing with this particular property typology. So this development is up in the Northwest, it's up in Manchester, and is part of a large estate. It came about through a conversation with the asset director at the RP about 3 or 4 years ago, and we were talking about different system build properties. Now, those of you who work with system built properties and also work with the wonderful RDSAP that generates EPCs will know that RDSAP treats all system built properties the same. And therein lies the challenge. They're not all the same. BRE have identified about 450 different types of system built property, you know, from the early 50s and before, right up until the late 70s. And they all have different building physics properties, and so we need to take a much deeper dig than SAP encourages us to. This project was a large estate built in 1970. About 40% of the overall estate was addressed by this project, but it began by just a conversation about how do we deal with these leaky concrete properties? That was the question asked to me. And my response was, are we talking about no fines concrete? For those of you who've come across no fines concrete properties, they are what they say. They're made from in situ cast concrete, cast in molds, very quickly, very rapidly built. And the concrete is basically missing the sand. So no fines means there are no fine particles. So it's in effect an in situ gravel wall solidified by a cement slurry with lots of connected voids. And the challenge that gives us is that these properties are super leaky from an air leakage point of view. The slide we're currently looking at is one of the most recent estates we've worked on. If you look at image 4, you'll see properties on the left-hand side and then the completed properties on the right-hand side, or at least the visuals thereof. And the challenge on this particular estate was manifold. Firstly, no fines concrete properties were just cold and damp, but quite well loved. We had a lot of residents who've lived there since the properties were built. They were decanted from Victorian back-to-back terrace estates, and then we've had a lot of long-term residents, and the houses are quite well loved in so much as they have really great space standards, and the layouts were good and they were pretty well designed. The problem being, it doesn't matter how much the central heating's on, the properties go cold as soon as the central heating's turned off. And that's because of the building physics of no-fines concrete houses. Our journey on these properties began back in 2014 on this kind of property. I should say there's about 300,000 no-fines concrete houses in the UK. Most of them under the management of registered providers and local authorities. So some of the lessons we can take from this series of projects are ubiquitous and deployable elsewhere. We began our no-fines journey working in Northern Ireland with Northern Ireland Housing Executive. For those of you who remember Retrofit for the Future, back in around 2010, there was a scale-up project around about 2014 that followed that. And we were fortunate enough to be designers on that work. Now, bear in mind, this was the early days of measured retrofit. We were only given 7 properties to look at, and we did them basically one at a time. They're in Antrim in Northern Ireland. We worked with Salford and Leeds Beckett universities and with BRE, and we had a deep delve into the building physics. We found these properties had a leakage rate of 16 and above, and when we took little bits of the wall away, we really started to understand how the building physics and air movement worked within them. If you imagine the external walls are about 300 mil thick. They have a pebble dash render on the outside and a batten and plasterboard on the inside, with all the services just running behind the plasterboard. Any air that's warmed up inside the property quickly goes through the plasterboard and through the sockets and into this honeycomb wall, straight up into the loft space and outside. Or as we found when we smoke tested one of these properties, straight into next door. So we had a neighbour coming and asking why smoke was coming from his plug sockets. And we to add to the complexity of the building physics, alongside Leeds Beckett, we did some heat tests through the walls, and we found that the U value could vary by up to 50%, depending on the density of the in situ concrete. So just what mix turned up on the day and how vigorously it was rammed into the mould would affect the U value. So these were quite difficult to model. So when we found a solution for the first 2 properties, we thought we dealt with the air leakage really well, and we found we had barely begun. We took the air leakage rate down from 16 to 14, and then did some modelling calculations, and we factored that 70% of the heat loss through the building was through air leakage. The impact of that was that if you then put external wall insulation, for example, on the properties, you may well, on paper, improve the U value, but you're really only affecting 30% of the heat loss. Of course, these properties as well were built on concrete rafts, so they have a lot of heat loss through the concrete slab. And if we traditionally apply external wall insulation and don't deal with the below DPC or the above eaves area, we're in effect just wrapping part of the wall and creating heat flows and air flows that again, we can't control. So what did we do? On the Antrim properties, it took us until the 5th one to really learn about the detailing in and around the eaves and the openings and the window installations, and the suspended floor, first floor, and also how the roof space worked, before we could get the air leakage rate down to where we wanted it to be. We managed to reduce that to, on the best property, around about 6, which was fantastic. Our target ultimately was 8. But then we took our knowledge to a second project. This was funded through National Energy Action. We started that in 2018. For us, we thought it was a massive scale up, 35 properties in Halton, in Merseyside. And we heavily monitored the work on this property to make sure, or these properties, to make sure the air tightness was where we wanted it to be. And we installed hobo data loggers. So we manually we manually installed the data loggers and collected them at the end of the project after a couple of heating seasons. And we logged the temperature and relative humidity in the properties. The documents from that are available if anybody's interested. But we managed to improve on our work in Antrim, really stabilize the temperature in the properties. But what we learned from that was a lot of people were not achieving affordable warmth before the works. And so as we also monitored the bills on those projects, the energy bills, we noticed the energy bills weren't going down, but the mean temperature in winter was going up from 14 to 21 degrees. What we learned from that was our residents had an energy budget and would achieve affordable warmth with that budget if we gave them the means to do so through fabric improvement. We also reduced the air leakage rate down to 5 in some aspects, and we were able to install mechanical ventilation and heat recovery and monitor the use of those systems. So if any of you were on the Retrofit Academy workshop this morning, we were talking about ventilation and how to improve air quality within properties. And we were also talking about the dichotomy between good ventilation and good insulation, in that we wrap these properties as tightly as we can in some instances, and then we want to extract all that warm air. So the heat recovery became important to us in the design of the Halton project. We monitored that for a couple of heating seasons, and we saw some really heartening results, and that then helped us further develop our approach to no fines concrete. One of the most interesting things to me is what you achieve when you deal with the building physics properly. So if we can properly wrap this leaky concrete, we can actually control the concrete and how it performs from a thermal point of view. So once the air is just moving around inside the concrete within the house, the concrete then acts as a heat store, almost seasonally, and also gives a homogeneous temperature through the property. So in effect, we're not just heating one room. When we heat one room, we're allowing that heat not just to percolate by conduction, but by convection throughout the property as a whole. So this slide really just shows the ethos of the scheme. We were improving, we were firstly minimizing the thermal bridges. This involved window replacement and treating reveals. I'll come to those a little bit later on. It involved wrapping the property in external wall insulation and extending the eaves. And on all of our schemes for no fines, we've insulated the slab edge, but haven't found the need to go below ground, which is always happy to take questions on that challenge. What we also did on a majority of properties was re-roofed, and that allowed us to do a couple of things. It allowed us to create a warm roof, which means that we don't have to ventilate at eaves level, which is super important when you imagine that this aerated concrete is open to just the inside of the eaves at eaves level, and really only protected originally by a layer of pebble dash. And if we don't cap the wall, we're going to lose all that lovely heat through air percolation. That allows us, of course, then to insulate at rafter level, which means we have a quite a nice wrapped internal space that's then ventilated by the MVHR, which is air filtered. And of course, we put as much insulation as we possibly could into these spaces. And we did some modelling around insulating at rafter and joist level. to see whether we were generating any condensation in the loft space. And that led to some principles that we've developed that we use in non-no finds properties as well. On a later project in Manchester, we weren't able to install the MVHR system for a number of pragmatic reasons. The Holton project was originally heated by a warm air system, which had long since been removed, but the ductwork and runs were still there, and risers, which allowed us to really easily bring some new ductwork through from the loft space. But in Manchester, we didn't have that luxury, but we found quite a decent direct MVHR unit with the heat exchanger within the unit, and we simply expanded the apertures from the existing bathroom and kitchen vents and install this unit. I'd like to find a slimmer one that would fit into a 110mm existing opening, but I haven't done yet. These are 150mm diameter, but they work particularly well on this project. And we moved to air source heat pumps in Holton on 30% of the properties, and in Manchester, I think on 70% of the properties. Again, there's a takeaway here. The original properties had hot water cylinders, which were subsequently removed when combi boilers were fitted over the last 20 years. And people do reappropriate space. If you have a cupboard that used to have a tank in it, it rapidly becomes storage for something else. And residents aren't always keen to lose that storage. For the properties that we insulated at rafter level, we were quite happy to put the tanks up in the loft and just work with the asset and maintenance team of clients to figure out how those tanks would be maintained. There's a piece of work that went alongside this on customer engagement on heat pumps. Yes, so and that piece of work was about behavioural change, and that encompassed the work we were doing to insulate the properties, how the properties then, the fabric of the properties became heat stores, and how those heat pumps would favour a lower temperature radiator system and would run not continuously, but for longer periods at lower temperatures, rather than the quick hit of a high temperature radiator system running from a gas boiler. We worked with a lot of the residents as well about removing gas cookers, which had a couple of benefits. It meant we could go completely off gas, and it also meant that we weren't producing pollutants from burning gas on hobs and in ovens in the properties. Current feedback is that the air source heat pumps are costing no more than the gas boilers. We are looking in all of our no-find schemes at augmenting air source heat pumps with PV arrays, which means that some of the electricity is generated on site, and that's further going to reduce the electricity bill. We think that'll tip the balance between the cost of gas versus electricity on these systems. So to run through the methodology, these aren't no finds for the experienced system built people there. This is a scan we did of some cross walls, but it's a useful scan just to illustrate what we can do from street side. So we're using a point cloud scanner, handheld, limited intervention to the residents are really rapid. We can pick up accurate dimensions of the properties. And from this, we make a process model. So we're using some software called ArchiCAD, which in some ways is similar to Revit, but it has some really nice inbuilt energy modeling potential. So we model these quite quickly from the point cloud, and we use this as the basis for all of the information we produce. It allows us then to do some thermal modeling. So this is a test of window positions in no finds housing. So the image on the left, and we do this live, so we can move the window around and find out where the sweet spot for position is. The image on the left was the existing condition, and you can see the white line, which is against the blue, is actually the dew point, the point at which condensation occurs. And in the current position, it's right up against the windowsill and the dry lining. When we add the external wall insulation, you can see that we push that condensation line out right outside the concrete. And to design this, we moved the window until that blue-white line was outside the existing building fabric, so that we could be sure that that concrete was going to act as a heat store and not be trying to resist damp. So modeling some of these, we tend to model in, we use all sorts of internal modeling software. So the modeling you saw on the previous slide is Eco Designer within the ArchiCAD suite. We also use Firm and PHPP depending on the project. We're obliged to provide data in EPC format as part of our projects. It's a system, whether we like it or not, that is there nationally, and it's how we compare one property to another. So we like our SAP modelling to be as accurate as possible. Like a lot of others, we might start modelling in RDSAP, but we export our RDSAP into on construction SAP, and that allows us to much more finely model cold bridging, window performance, and any of the technologies that we put in. One of the things about RDSAP that's worth mentioning is you can see in the bottom left image, the wall type is system build, and that will trigger a whole series of variables to be filled, regardless of whether your property is no fines concrete or BISF steel frame, or cross wall and timber frame. So we like to expand on that and get much more detail in. But you can see from the top left, the starting point was an E52. Through the non-renewable work, so fabric only, we got these properties up to a C78, and we reduced the heating load from over 200 kilowatt hours per meter squared per annum to just under 50, which was what was called for in the demonstrator phase. Going forward, with the introduction of renewables, particularly with PV, we were getting to a level of above 90. This modelling doesn't take into account the fact that we've turned some leaky concrete into a nice solid heat store. So I would expect the actual performance, if modelled and measured properly, would be pushing 100 once the PV is installed. So next, once the energy modelling is done and we've identified the measures, we then introduce all of the measures onto the model. We tend to pre-program these at the beginning of, if it's a large-scale project, we'll pre-program all of the parameters and elements that we're adding, and that will drive the drawing issue and quantities that our contractors use. So a drawing pack might look something like this. This is the ground floor. If I were to go back and move a light fitting or move a door or move a wall in the model, the drawing pack would update similarly. Here's the first floor, and you can see where the existing boiler is and where we're removing that, liberating some space that can then either take a tank or become some storage space. And the notes are parametric as well, so they're generated from the library items that we put onto these models. We like to cover all the enabling works. For those of you who are delivering retrofit schemes, you'll know the first time you do it, you cost up your EWI and cost up the PV and cost up various interventions, and then you find the cost doubles because of all the enabling works like extending eaves, repairs, finding out that when you take your windows out on no fines, for example, the apertures are not only not rectilinear, but they're not perpendicular from front to back either, because the whole thing was cast in molds and having to deal with that work. In fact, we're working on some no fines at the moment in Wolverhampton, And it's always good to be on the ground talking to your residents. We found from one resident who's been in his property for 50 years that our window replacement this time around would be his fifth set of windows. So if you imagine that windows have been fixed 4 times previously into some non-reinforced aerated concrete, you can imagine the kind of issues we find when we take the windows out and what's been covered up in the past and what needs to be rebuilt. So on our next project, we're going to design some cassettes, insulated cassettes that will fit into these window openings and receive a more standardized window. So we are still learning as we go. We're on No Fines project number 5 now. Final set of drawings has all the site notes that are needed, plus quantities, plus references to a detail pack. And we like to produce a summary model. So one of the benefits of modeling all these things in 3D is we can produce a cutaway model that we use for engagement, whether that's internal in our office or with our contractors or with the registered providers, or most importantly with the tenants, where we can explain exactly what's happening to a property, why it's happening and what the outcome is going to be. And we found that engagement actually is really useful in fomenting the behavioural change that's needed when a resident goes from living in a historically leaky property, where you might spend your evenings in one room trying to stay warm, to a house with a homogeneous temperature and stored heat within the walls that actually act as low temperature radiators in themselves. The finished product, this is the Manchester scheme again. Manchester was also part of a larger new build scheme, and we wanted these properties to look as good as the new build properties. So we worked with the designers on those to make sure that was the case. We had a single pallet of materials, worked with the planners, and this served to remind us that really at the end of the day we are architects. We are dealing with properties that have architectural merit, and the finished product shouldn't just deliver better building performance, but also it is part of a wider public realm and has a place in that. So I've probably only touched on 30% of all the thinking that went behind those projects.